What is up, YouTube? This is Mr. Kane coming at you live from the studio. Here is what we're doing today. We are gonna go over the answers for the practice final for physics. All right, get comfortable. This is gonna be a long video. First thing, according to Table 1, describe the relationship between force and acceleration. So I want you to notice. In Table 1, we have force changing and then the acceleration of the car over time. So you should notice, as force increases, so does the acceleration. So as the force increases, acceleration also increases. Alright, next. According to Table 2, describe the relationship between mass and acceleration. So in Table 2, the mass is changing now. So as the car's getting heavier, the acceleration is slowing down. And that's like in real life. Things that are heavy have more inertia, so they're a bit harder to get to go fast. So, as mass increases, it's the opposite. Acceleration decreases. Alright, next one. You need to know Newton's second law, which is force equals mass times acceleration. And if you do some algebra, you can rearrange it and divide to get acceleration equals force divided by mass. So, to get part C, if a cart weighs 1 kilogram and was pulled by a net force of 16 newtons, to get A, you do 16 divided by 1, which is equal to 16 meters per second squared, or meters per second. That's how you do C. Part 2, a frictional force of 6 newtons was acting in the opposite direction. Okay, so if you're going 16 newtons one way, and then 6 is pulling you back, you do 16 minus 6, since it's going the opposite way, and the total net force, the overall force and the net force is going to be 10. Okay, so 10 newtons, and since the cart still weighs 1 kilogram, 10 newtons divided by 1 kilogram will be 10 meters per second. So it's 10 for that one. D, consider a 0.5 kilogram cart traveling at 2 meters per second, hitting another 0.5 kilogram cart that is not moving. Remember, momentum equals mass times velocity. Before the collision, what is the momentum of cart A? Before anything happens, okay? What is the momentum? So momentum is mass times velocity. So it weighs 0.5 and it's going 2 meters per second. So 0.5 times 2 equals 1. And if you're curious, it's just the units for mass times the units for velocity. That is the units for momentum. Next, before the collision, what is the momentum of cart B? Cart B now. B is not moving. So the mass is 0.5, but the velocity is 0. So that's 0. Since it's not moving, there's no momentum. Next one, after the collision, car A stops completely, and car B now travels backwards at 2 meters per second. Was the momentum conserved in this collision? How do you know? So you may notice car A started out at 2 meters per second, and then car B ended up going 2 meters per second. Okay, so clearly all of the speed and momentum from car A went into car B. So the momentum is the same as car A was. Momentum is 2 times 2 meters per second, velocity times the weight, 0.5. You get 1. So momentum was conserved. All of the momentum from cart A went into cart B. That's the idea. Conserved just means it all stayed the same, but it may have just changed into a different form. This next one was pretty tough for some students. A bungee jump prototype with a mass of 0.5 kilograms is dropped from a desk. Fill up the table in order to solve for the maximum potential velocity just before it hits the ground. we may use G equals 9.8 meters per second squared. Okay, so you start out with 1 meter up. And remember, the equation for potential energy is mass times gravity times height. So the mass is 0.5, gravity equals 9.8, and the height is 1. Okay? So that math is a bit easy on purpose. The mass is 0.5, gravity is 9.8, height is 1. So the potential energy is 4.9 joules. I can prove it on the online calculator. So our height was 1, the acceleration of gravity is 9.8, and it weighs 0.5 kilograms. So that's how many joules of potential energy is. And for the kinetic energy, I didn't give you the velocity on purpose. You need to know that in the beginning, the bungee jumper isn't moving. So since V equals 0, there's no kinetic energy. So the total energy is 4.9. Now, at a height of 0.5, half of the energy went into kinetic energy, because now you're halfway. So it should be half of 4.9. Okay? Half of 49 is 29.95. That's not 49, it's 4.9. I can try and do it on the calculator too. 0.5 times 4.9 times 0.5. Oops. 9.8, the acceleration of gravity, times the height, 0.5, times the mass. Okay, 2.45. Oops. Got that one wrong. Oh well, that's why you double check your work. So I took the acceleration of gravity times the mass times the height. Okay? And I still don't know the velocity, but you should know that energy is conserved. So the total energy has to be 4.9. So what we do is the other energy that was lost went into kinetic energy. So the other half went to 2.45. Next one, the hint for potential, it's on the ground, so the height is 0. So potential energy is 0 joules. And since the max speed is right before you hit the ground, all of the energy went into velocity. So those are the answers. Okay? Next one, explain why Newton's cradle cannot continue to swing forever. Hint, think about a force that starts with an F. Okay, so you may have seen Newton's cradle before. It's the balls that hit each other and they go on forever, in theory. And my question is, why does it stop eventually? So it'll go on for a while, but eventually something called air resistance and or friction will slow down. The friction will slow down to a stop because it acts in the direction opposite to movement. So friction is what's always slowing something down. Next one, nuclear processes. Construct a CR that makes a claim about whether or not C14 above would be a useful isotope to use in dating a 100-million-year-old dinosaur bone. Your argument should include the following evidence from the graph. The half-life of C14, and explain whether you can use C14 based on the half-life above. Okay, so first saying half-life is the time it takes to go to half. So if we start at 100%, it goes to around 50% at this red dotted line. And I'm going to say that's around 6,000. Half-life is 6,000. Right here, I'm going to say that's 6,000. And since the half-life is so small, 6,000, and the dinosaur bone is 100 million years old, all of that carbon-14 is probably going to be gone. Almost all of it. There will be still a small amount, but most of it will be gone by that time. So since the half-life is so small, most of the C14 will be gone by the time it takes for 100 million years to pass by, since that's going to be a lot half-lives within that 100 million. So C14 is not useful. In reality, you want something with a half-life close to the fossil you are trying to date. Okay. Next one is from your notes, write the three variations of the wave equation. C is the speed of light. Lambda is wavelength. Hopefully you have that in your notes. F is frequency. Using the appropriate equation, determine the frequency of a radio wave with a wavelength of 500 times 10 to the power negative 9 meters. Recall that all forms of light travel at the same speed. 3 times 10 to the power, that's frequency. That's what I'm looking for. I know that the speed of light is 3 times 10 to the power of 8. And I know from the problem the wavelength is 500 times 10 to the power of negative 9. 500 nanometers. Hopefully you have in your notes the formula. Remember, C equals wavelength times frequency. And if you rearrange it, frequency equals C divided by wavelength. I didn't want to copy and paste the lambda. So you take the speed of light, 3 times 10 to the power of 8, in parentheses, divided by 500 times 10 to the power negative 9. And that'll give you the frequency. Remember, your frequency should be very big. Three times 10 to the power of 8 divided by 500 times 10 to the power negative 9. And your answer for frequency should be 6 times 10 to the power 14 hertz is the units. The E, the times 10, doesn't really fit on the calculator well, so they just put E. And that really just means 6 times 10 to the power 14. So that's your answer. That is the last one. That's the frequency of that wavelength of light. And that's the last one. Thank you so much, everyone, for staying with me. Have a great night. Best of luck on your finals, everyone. Bye.